NPTEL course on computational fluid dynamics. I am Krishna M. Singh from Department of Mechanical and Industrial Engineering, IIT Roorkee. In this course we will have a fabulous journey to the fascinating world of the computational fluid dynamics. We will have a look at all the aspects, theoretical, numerical and application aspects of computational fluid dynamics, which will enable you to apply it to solve myriad problems in real life. In the first module, we will have 2 lectures wherein we will provide a brief introduction to computational fluid dynamics. We will briefly touch upon the basics of what we call computational fluid dynamics. We will have a brief look at the historical perspective, how this method evolved and how this particular branch of computational mechanics has evolved over the time, and we would have a look at what are various applications wherein CFD is being used in industry as well as in research. Thereafter we will have a very brief look at the numerical simulation process, which is at the heart of CFD, and what are the main discretization techniques which are used in CFD, and then we will also briefly tell you the outline of this whole course of around 40 to 42 lectures. What are different topics which we are going to cover in this introductory course? This is what we will have a look at in detail. So in the first lecture we will cover the basic introduction to computational fluid dynamics, historical perspective and applications. The remaining 3 topics we would cover in the next lecture. So now let's have a look at the basics of computational fluid dynamics. We will have a look at the background, how this particular branch has evolved, what is its application, where does it stand today, and what is the connection between what we call computational mechanics and CFD, how are these 2 specialities are related to continuum mechanics. Then we will have a brief historical tour of the evolution of computational fluid dynamics, and then we shall have a look at few important applications of CFD. Now, background of the CFD, let's have a look at what is our main objective as engineers or physicists. We want to analyze a physical problem, and we can tackle physical problem in 2 ways. First, what we call physical modeling, which would involve experimental analysis, wherein we will build the prototypes of a physical system, instrument it, collect data and analyze what is happening in different parts of the system under different operating conditions, or what we call environmental conditions. The other part, the way we can analyze a given physical problem, is to come up with a mathematical model which will result in an integral or differential equation. This integral or differential equation may not be amenable, in fact most of the time for real life problems it is not amenable to what we call closed form analytical solution. Then the recourse is that we can go for approximate numerical simulation, and this particular aspect has picked up specifically in past half a century with the developments in computer hardware and computer science. So let's have a look at the interrelationship between both of these approaches to solve a physical problem. So we are given any problem. This physical problem could be from any branch of physics or mechanics or engineering. Now there are 2 approaches. The first one is, as I discussed, that we can come up with a model, we can fabricate a model of a physical system, instrument it and perform what we call experimental analysis, collect the data, interpret the data and thereby come up with the conclusions about the physical behavior of the system. The second aspect is we make a mathematical model and try to perform analytical analysis if we can. If analytical solution is not possible, we can also have a numerical solution. And the way these arrows indicate that both of these physical modeling, that's experimental analysis, and mathematical modeling, they both support each other. They do not exist in isolation. One is not a replacement of the other. This point I would like to emphasize to any budding physics engineer or an analyst, that please beware, we cannot do away with either of these techniques. We need both of them together. Physical modeling or experimental analysis is a must to verify or what we call validate the numerical solutions, and the numerical solution can also give us an indication that how we can come up with a better physical model and how we can improve upon our experiments. So these are always used to supplement each other. So both of these approaches would supplement each other in tackling or in solving our physical problem. Now this physical problem could relate to the design, it could relate to the analysis of some problem which we have observed in the existing system, and so on. So whatever might our physical problem be, we would use in real life both these approaches in harmony. Now let us have a look at the aspects or features of each of these two approaches for the analysis of a physical problem. First, about physical experiments. Now physical experiments are usually very time consuming and expensive to set up. We have to come up with a model, physical model must be fabricated. We have to instrument it, and we have to come up with what we call fairly costly equipment to set up the measurements. The measurements must be set up in a very controlled environment. So all of these aspects consume lots and lots of time, and it has to be repeated for each system or subsystem separately. And usually it is not possible for us to perform the experiments on the actual prototype. We cannot perform experiments on, let's say, an actual full size car or a train or an airplane. So what we normally do in the physical experiment is that we come up with what we call a scaled model, which is a much smaller geometric model of our actual system. The measurements are performed on this model, we obtain certain results, and there are limitations on the extrapolation of these results which we have obtained on the scaled model to the actual prototype. They are both kinematic as well as dynamic constraints on this extrapolation process. So that's it and the limitation of physical experiments. At the same time, the experimental data is the one which provides us with the closest possible approximation of the physical reality within the limits of the experimental errors. We do not make any assumptions regarding the variations of material properties or what we call constitutive models. In our experimental simulations, we would mimic the way our actual system or prototype is supposed to work. Similar sort of conditions we would normally mimic for experimentation on a scaled model. So that's why experimental data is very crucial, and it provides us with what we can call the closest possible approximation to the physics of the problem or what physical reality of the problem. Of course, we should also be aware of the limits of experimental errors. There are errors involved in each measurement process, but notwithstanding those measurement errors, the experimental results provides us the best possible approach, a best possible approximation of the real physics of the problem. So that's why even if we can come up with a mathematical model which can be solved analytically or numerically, we ought to verify or we ought to validate our mathematical model with the results obtained on the scaled model through physical experiments. So physical experiments are very, very crucial in our understanding of a particular system. Let us have a look at the modeling and simulation approach. Now when we come up with a mathematical model of a physical system. Say let's say we want to find out what happens about the flow around an aircraft body, we make a set of assumptions regarding the variation of the problem variable, at which are the variables or which are the flow parameters, say for instance in the case of an aircraft problem, are important, which we need to analyze. Constitutive relations, that is to say in which way different variables of the problem are related to the material properties. How do the material properties themselves vary? So we make suitable assumptions regarding these aspects. So the mathematical model which we obtain may not be an exact representation of the physical problem. So there are approximations involved in the mathematical model. Moreover, if a mathematical model cannot be solved exactly using analytical tools, we have to go for what we call numerical simulation, and we will see very clearly in this course when we develop various numerical simulation scheme, we will clearly see that numerical simulation process introduces additional errors in the solution. So irrespective of the beautiful software which we might have for modeling a problem or for solving a problem, which can provide us very beautiful graphics, and what it can claim that if you got powerful enough computer system we get very accurate results. Nevertheless, the mathematical model which is basis of that software and the numerical simulation process using which we have obtained our solution, they both involve certain approximations, and as an analyst, whether you are a physicist or an engineer, we must be aware of the errors involved in modeling and simulation. So that's the reason why the results of any analytical or numerical study must be carefully validated against physical experiments to establish their practical usefulness. If we cannot do this, we cannot extrapolate or we cannot use the results which we have obtained from the numerical simulation for real life design applications. We will always have certain doubts in our mind whether the assumptions which are made, they are good enough to give us a workable approximation of the physics of the problem. But this one plus point here, that once we have validated our numerical model using the results from the physical experiments which would have usually been performed on a scaled model, so we are no more bound by the constraints of the geometry in computer simulation. There are limitations on a physical experiment that we cannot perform physical experiments on the full size prototype of an aircraft or car or train. So we have performed experiments because of these constraints on a scaled model, use the results from a scaled model to validate our numerical simulation process. We have taken the same physical model, a scaled model, we will model it in the computer, what we call solid modeling, we will come with geometric model. We will use our mathematical model for this particular geometry and obtain our numerical solution, validate this numerical solution using the results on the scaled model obtained experimentally. So that is what would validate our numerical simulation process. Once that is done, we can change our geometric model in the computer, we can come up with the full scale prototype of the plane and can obtain the results on our full scale problem. So thereby we would eliminate the need of extrapolation. So whatever additional errors might have been incurred because of extrapolating the results on scale model to full scale prototype, that is simply eliminated using computer simulation. So that's the beauty of the computer simulation. Not just that, there are situations wherein, or there are physical problems for which we cannot come up with an experimental model or physical experimental model. It might be too dangerous, or it might be outright impossible. For instance, we have, let's say, we want to simulate loss of coolant exchange situation in in a nuclear reactor. It's very difficult to come up with a physical model of a radioactive reactor and perform this loss of coolant exchange situation. But there is no such limitation in our computer model or numerical model. We can model the full scale nuclear reactor and try to see what happens if there is loss of coolant exchange situation, to see how the things change, how the temperatures shoot up in the reactor core and so on. So there are many such situations which cannot be where it's too dangerous to come up with a physical model. They can be easily done, or we can come up with a computer model and obtain insights into the working of that system in certain situations. So that's the beauty or that's the advantage which we have got in the numerical simulation process. And that has been one of the reasons why in past 6 decades there has been tremendous progress in the branch of mechanics which we call computational mechanics, and this has been closely associated with the advancements in the computer science, both in software and hardware side and applied mathematics. So what is computational mechanics? Mechanics is a branch of physics. What does this additional prefix computational mean here? We already know if we have got a physical problem, we can come with a mathematical model, and mathematical modeling of a continuum problem, it leads to a set of differential, integral or integral differential equations. Which type of equation we will come up with, that would depend on the mathematical model which we have used and the physics of the problem. And exact analytical solution of such equations is limited to the problems in very simple geometries for very simple variations in material properties. We have to assume material property to be either constant or this should be linearly varying or so on. So there are very limited set of situations in which we can obtain an analytical solution to a problem. So for most of the problems of practical interest, specifically for engineering systems, an approximate numerical solution is sought. And in the context of mechanics, we can put it as the science and practice of obtaining approximate numerical solution using digital computers is termed computational mechanics. So remember, there are two words here, the science and practice. So the computational mechanics is a science, at the same time it is also an art form which comes up with a practical experience. So science and practice of obtaining approximate numerical solutions using digital computers for the problems in mechanics, that's what we will call computational mechanics. And in case if you are dealing with thermofluid problems, that is the problems involving fluid flow and heat transfer, this approach is termed as computational fluid dynamics. So now let us try to put a formal definition of computational fluid dynamics. So what is computational fluid dynamics? If that is your question, let's try and answer that formally. So the computational fluid dynamics is essentially a branch of continuum mechanics which deals with numerical simulation of fluid flow and heat transfer problems. So all said and done, it is a branch of physics, in particular the branch of computational mechanics, but the focus is on the problem which involve fluid flow and heat transfer. So the heat transfer does not appear explicitly in the name which we have given computational fluid dynamics, it is always there, it is intrinsic part. Heat transfer problems form an intrinsic component of the branch of computational mechanics called CFD. So let us repeat once again that computational fluid dynamics is a branch of continuum mechanics which deals with numerical simulation of fluid flow and heat transfer problems. Now what do we do in computational fluid dynamics? We basically try to find out approximate numerical simulation of governing equations of flow problems based on fundamental conservation laws of physics, namely mass, momentum and energy conservation. So, there are three laws based on which we would obtain the mathematical model of a problem, and we would solve it approximately using digital computers to obtain the solution of a problem. In particular, we will get the distribution of the flow field, temperature distribution, density and pressure distribution for our flow system. I would once again like to emphasize that although word heat transfer is missing from CFD, heat transfer is an intrinsic part of this discipline. So, thus we can summarize what CFD involves. The CFD analysis involves conversion of governing equations for a continuum medium into a set of discrete algebraic equations using a process called discretization. The computers can only work with discrete numbers. Okay. They cannot solve our continuum problem as such, but they are very powerful to deal with what we call number crunching. So, the first process which CFD analysis would involve is to convert our continuum governing equations into a set of algebraic equations, and this particular process is referred to as discretization. That is to say, we have converted a continuum problem into a set of discrete problems, and once we have obtained the discrete problem, solve the system of discrete equations using a high speed digital computer to obtain the numerical solution to desired level of accuracy. When we are talking about desired level of accuracy, this accuracy refers to the solution of the discrete equations. It does not refer to the solution, overall solution of our continuum problem per se. Now, we have defined what we mean by CFD and what in nutshell the process involves. Let us have a look at the historical perspective, how CFD evolved, what led to the developments in CFD. And we will see specifically when we start off in our next few modules our discussion of finite difference methods, we will come across certain techniques whose development dates back to pre-digital era, maybe few hundred years back. So, that is regarding our finite difference techniques and some of the difference schemes. They are linked to the name of Euler few centuries back. But when it comes to computational fluid dynamics, the history of CFD is intrinsically linked to the advent of high speed digital computers in late 1950s. Now, there is a big debate in CFD community as to who were the first one, that whenever something is invented, something is established, who were the first one who did the first CFD simulation of a flow problem. But we will not go into these details in our discussion today. We will not get caught into this debate. We would rather focus on the interesting developments from motivational and application perspective. So, we would not look into the chronology, that is who were the first person who performed a CFD simulation of a flow problem, or who were the second person and so on. We will look at how the CFD evolved to motivate us for our course, and what are the applications wherein we can apply CFD as physicists and engineers. So, that is where our focus would be. So, let us have a look at the early applications. And early beginning of the CFD can be traced to numerical simulations for aerospace applications. In fact, in most of the physics and engineering, the major breakthroughs or major developments were linked to what we call military superiority or developments in for defense applications, and CFD is no exception. So, here again the first simulations were tried for the fighter planes, okay, and thereafter for the passenger planes. So, the early beginnings were linked to the aerospace industry, and developments were made at Douglas, Boeing, NASA and Lockheed Martin in 1960s based on a method which is called as panel methods, wherein the body of an aircraft is broken into small sub panels, and there are certain distributions are assumed for some functions in terms of which we can construct our flow field. So the panel methods were the first ones to be used for the flow simulations over an aircraft body. And you will be surprised to learn that the codes which are based on panel methods and their improvements, which were developed in late 50s and 1960s, they still play an important role in design of modern day aircraft, whether it is a fighter aircraft, a passenger aircraft, or a freight liner. So the first design we would use for analysis, for a quick analysis, we would use panel methods. The next early applications were made in meteorology. So meteorologists were the next user of CFD for weather forecasting applications. In fact, we will have a look at one particular methodology for simulation of turbulent flows, which is called large area simulation. And large area simulation models, they first appear for modeling atmospheric boundary layer, that is to say for modeling of atmospheric turbulent flows in early 1970s. So these were two main industries in the early era, that is in 1950s, 60s and early 70s, for the developments in CFD. Then let us have a look at the algorithmic developments, because just the progress in the computer hardware was not enough. We needed many algorithms to discretize a continuum problem into a tractable discrete problem which can be solved using a digital computer. So there are many algorithmic developments in CFD front. So 1960s saw the development of particle in cell method, marker in cell method, and vorticity stream function methods at NASA labs. In 1970s, these developments spread further, and there was one school or research group led by Professor Brian Spalding at Imperial College London. They came up with the development of what we call parabolic flow codes, which were named as GenMix. This happened in early 1970s. Vorticity stream function based codes were also developed at Professor Spalding's group, and a simple algorithm. So these three developments, which were done by Professor Brian Spalding and his student, most notably Professor S.V. Pattankar, who was the architect of simple algorithm, that can be said to be a watershed event in the development of CFD, because that led to the widespread applications of the use of CFD techniques for solution of Navier-Stokes equation, that is the full scale flow and heat transfer problems. Because earlier methods which were used in aerospace industry, the panel methods, they were based primarily on Euler's equation, and in contrast to that, Professor Spalding's group provided the first thrust towards the developments in viscous flow and heat transfer problems. And in 1980s onwards, there was vigorous research activity in various parts of the globe addressing different aspects of CFD. By now, CFD was recognized to be almost at par with what was referred to as finite element analysis in structural applications. And in fact, the developments in finite element analysis, computer aided design, and grid generation, specifically the unstructured grid generation, led to the vigorous development in computational fluid dynamics as well. So since then, the research work has been going on in all parts of globe. It's not localized just in Europe or USA. It's in every nook and corner of the globe. There are vigorous research activity addressing different aspects of CFD, notably development of new discretization methods, new models to deal with the turbulent flow situations, newer numerical algorithms which can give us more accurate and faster solution to our discrete systems, and these will also be robust methods. Grid generation methods, which are specifically important for three-dimensional problems in complex geometries. And from practical perspective, we also need to visualize the results from the CFD analysis. The CFD code gives us the flow variables at millions of discrete points. Just having those numerical values does not give us a complete understanding of our system. So post-processing tools which have been developed recently and visualization tools, they help us in understanding the physics of the problem using our numerical simulation. In last 2 or 3 decades, there has been it in the thrust, that is in parallel implementation, especially when the parallel supercomputers have become commonplace. Till 1980s, these parallel computers were the pressure only of very large research labs in USA or Europe, or Japan, but recently they have become more widely available. So there has been lots of research going on regarding implementation of the CFD algorithms on these parallel machines. Most recent advent in this area is the use of graphical processing units, which we have been using for playing games long since maybe past few decades. Can we use those GPUs which have got tremendous processing power which they use in 3-dimensional games? Can the same power be brought to use in the simulation of flow problems? And from an engineering perspective, let's have a look at the way the things came into being regarding computer-aided design, which led to the industrial applications of CFD. So industrial applications of CFD have been boosted by availability of commercial CFD codes in 1980s and their integration with computer-aided design and stress analysis codes, most notably the ones based on finite element analysis. So developments in computer-aided design and finite element analysis, they have inspired developments of commercial CFD codes with user-friendly graphical user interface, and most of these commercial CFD codes, they provide their own inbuilt solid modeling software and very powerful visual post-processing capabilities. They also offer full interoperability with various CAD systems that you might have used CATIA, ProEngineer or SolidWorks to come up with, let's say, geometric model of your aircraft or your high-speed train over which you want to analyze your flow field. Now those models which you might have spent considerable amount of time developing on your favorite CAD system can be transferred directly to your commercial CFD software, wherein you can perform the further modification steps. Maybe there might be some geometry patching to need to be done to make the geometry more amenable for flow analysis. We will perform grid generation, and thereafter our CFD software can be used to come up with the flow solution. Once the flow solution is available, we can analyze the velocity field, the pressure field, the drag which is being generated, and how we can modify the geometry to reduce the drag, specifically let's say from transport applications. That data can be fed back to our CAD model. We can change our geometry, and the change geometry, once we are satisfied in our design cycle that we have got, or we have come up with the geometry of a transport model with this plane, a car or a high-speed train. So we now come up with a fairly what we can say a final design which meets our requirements that can be directly transferred for production software or CAM systems. So in this way, recently there has been in industry attempts being made to integrate CAD systems, finite element analysis systems which look at stress analysis, and the CFD software in one big integrated applications to enable the completion of industrial design cycle and thereby obtain the designs of our products rather quickly and without making any errors due to transfer of data from one system to another. And availability of commercial as well as open source GUI based codes which offer CAD interoperability has now led to what I would say the complete integration of CFD in design cycle. Next, let's have a look at the applications of CFD. Why do we need to learn this particular branch of mechanics? What are its use? So if you look at its potential applications, I have just mentioned a few of them in a historical perspective section, but now let's have a look at few other applications which will motivate us to learn this art and science of very interesting, exhilarating and demanding branch of the fluid dynamics called CFD. And let's note here that CFD is being used for both fundamental research. Fundamental research is being carried out to understand the flow of physics in various systems at various length scales, starting from the planetary to intergalactic, from intergalactic to planetary to what we call micro scales. Okay, so that's the fundamental research aspect. Similarly, CFD is now being used thoroughly in industrial R&D cycle for both design applications as well as for what we call troubleshooting aspects. So CFD analysis forms an integral part of design cycle in most of the industries now, from aerospace to chemical to transportation to biomedical engineering, and it's one of the most exciting areas from the human perspective, it's biomedical engineering. And the length scales which I just mentioned earlier, they can range from the planetary boundary layers to microchannels and electronic equipments. Metrologists were the early users of CFD software, or they were the ones who contributed to development of what we see the science and art of the CFD today. And every day you will see on a television screens or in netcasts various beautiful graphical pictures of weather forecasts. Now how these forecasts are made, at the backbone is a CFD software, or maybe a set of sources, what we call CFD systems. And this weather forecasting is one area wherein the physical modeling and numerical simulation, they are used together. We have got weather balloons, we have got weather stations which keep feeding the experimental information to our forecasting stations, and there this information is fed as initial air boundary conditions or initial and boundary conditions to our numerical simulation systems to obtain short term as well as long term weather forecasts. And that is one of the reasons why you will see that forecast keeps changing. Let us say the forecast which is done in morning for some area, if you look at the same forecast from same agency in the afternoon, there might have been a change. The reason is very simple. Newer data was fed in from our physical measuring stations, or what we call weather stations, into our numerical modeling software. The CFD software took cognizance of that data and gave us what we can say a more accurate near future forecast for the weather. So this is one of the most exciting application areas of meteorology of CFD, which is our weather forecasting. Aerospace industry, which I just mentioned, we saw in our historical section, this was the first one to use the computational fluid dynamics. It's also one of the biggest uses even today, and the CFD is used from design of wings to the complete aircraft aerodynamic design. So design of all the subsystems of an aircraft, CFD is used thoroughly. It could be wings, it could be body, or it could be the turbofan engines which power an aircraft, and same holds good with the spacecraft designs as well. Turbo machines, we have got a variety of turbo machines. They could be hydraulic, steam, gas, or wind turbines. We can also have, we have got pumps of various types, we have got compressors, blowers, fans, diffuser and nozzles. All of these machines wherein the flow is very important. CFD is being used to analyze these systems, to come up with a weighted design and to troubleshoot if there are any problems in these turbo machines. Similarly, CFD is also being used extensively in the design of engines. It could be internal combustion engine, they could be gas turbine engines. So for combustion modeling as well as for the flow through a turbo machine, for all these complete aspects we have numerical simulation models available. For combustion modeling we have to supplement the flow physics from the chemical kinetics of the combustion process. So this is another exciting research areas of CFD application. Design of electronic systems. Every day the chip makers are coming up with smaller and smaller microcircuits or integrated circuits with huge billions and billions of processing units which are built into this very small area, and cooling of these circuits is one of the major concerns in electronics industry. So can we come up with a numerical model to understand the process of heat generation, the way it is diffused, it's being diffused across the circuit, and what could the possible cooling solutions be, how well a particular cooling approach would work and so on. So if before we actually design these circuits and the cooling systems, numerical simulation can be performed to understand which particular approach would work the best and will keep our integrated circuits in good health. Chemical process engineering is using the CFD modeling extensively to model almost all types of mixing processes and so on. CFD is also being used for the analysis of variety of engineering systems. They can range from the thermal power plants to nuclear power plants to the wind farms to solar systems and so on. We can also perform the modeling of accident situations for nuclear reactors using CFD, which are very difficult to do otherwise using physical experiments, to understand what would happen in case of an unforeseen accident. So CFD analysis can be used to forewarn us that what would be the situations which would arise in accident situations and what sort of measures should be taken or should be built in the design of our nuclear reactors. Understanding of the flow physics in nature is also one of the most exciting application areas of CFD, specifically for civil engineers and hydrologists. They would like to have a look at the way the flow takes place in the rivers, how do the rivers change their course during time, how do various canals and channels they work, like how the flow works there. If we have got bridge pairs, how the flow is affected by the bridge pairs, or how the bridge pairs should be designed to have the minimal effect on the flow, how the flow patterns affect what we call local environment ecology, because these natural systems like rivers, channels, ponds, they also have a thriving ecosystem, and the flow patterns, understanding of the flow pattern is also important to understand the ecosystem and maintain its balance. Similarly, how the flow takes place in ground aquifers, how the sediment is transported across a river or a canal, these are all very important aspects from the civil and ecological perspective, and this in these areas CFD is being used extensively to support the physical experimental modeling. And the area is relevant to what we call heating, ventilation and air conditioning for very large commercial hubs, or maybe let us say for hospitals, for labs. We have to come up with the proper design of ducts, that where should ducts be placed, where we should have the placement of heating ducts or cooling ducts for optimum comfort level, in our building, so that we can predict or we can come up with an alternate designs of our HVAC system before actually installing our heating, ventilation and air conditioning system, so that we can have optimum cooling and heating provided in our building. Surface transport is again the heavy user. We have already seen one version of this, so we have already seen its cousin in aerospace industry. The same techniques are also being used in the design of cars and high speed trains, what we call aerodynamic design of vehicles. It is also being used in design of the marine systems, hydrodynamic design of ships. We can also use CFD to work on the loads on offshore structures. For instance, we have got oil exploration rigs which are anchored in the sea. There also we can use a numerical simulation to predict the loads on these offshore structures and thereby come up with a robust design of these structures. And one of the most exciting applications in the past decade or so is application of CFD for biomedical problems. The prominent applications have been made in simulation of blood flow through arteries and veins, fluid flow in renal and ocular system, and drug delivery aspects. In fact, the recent trend is to perform what the doctors say a patient specific simulation. Now, before a doctor wants to perform, let us say, cardiac surgery or a bypass surgery for a patient, he or she would like to know that how is the blood flow in obstructed mode or in diseased condition in the patient. So we can have CT scan of the patient body. Using CT scan and synthesizing systems, we can come up with a geometric model of the complete cardiovascular system. That cardiovascular, the model which we have obtained, can be simulated using a CFD software to see which are the areas of obstruction which the doctor needs to focus on, where should be the ideal placement for the bypass and so on, or in case if it just the operation is being performed to remove certain obstructions, where those obstructions are and what would be the best way to tackle them. So this patient specific simulation can help a doctor to plan the operation for a patient very meticulously. Similarly, the drug designers can also understand that when a particular drug is being fed to a patient, how effective would be the drug could be fed, let us say, using a capsule or a tablet or an injection form, which mode works in what way, how the chemical drug is being transported by your blood to the place in the body where, or the targeted place in the body. So we can just have a much better understanding of a drug delivery system. We can come up with a better design for the stents, that what should be the design of a stent for a particular patient even. So if you got the CAT data of a CT data of a patient, that data could be used to design good stents for the particular patient. So there are tremendous research work which is going on in this biomedical area. It is also one of the most complicated ones, because here one has to collaborate between the people from diverse background. We have to collaborate with the doctors, with the patient, with the people from the animation industry who can give us a synthesized version from the CT scans. We need computer graphics experts, we need the experts in flow simulation, we also need experts in what we call biomechanics to help us understand a particular situation or understand what is happening in the cardiovascular system of a particular patient and so on. So this biomedical applications is one of the most exciting research areas today, with applications of CFD. And I would also like to put in last fundamental flow physics. We would like to understand the dynamics of laminar, transitional or turbulent flows in different geometries, and to understand this flow physics, numerical simulation can play a very vital role, specifically with regard to turbulent and transitional flows, wherein the planning of experiments for complex geometries might be pretty difficult. So if we can perform very fine scale or fine resolution direct numerical simulations, they can give us very good understanding of the physics of the flow in a particular situation. So I have just listed few very prominent application areas which I hope would motivate you to learn the science and art of CFD, which you can use for your industrial problem, or if you planning to have a research career in CFD, you can already see that we have got many exciting and challenging problems in all branches of physics, engineering and biology, wherein you can apply your knowledge of CFD to contribute to the design of newer systems, to design of better health monitoring systems, or better you can provide help to the doctors to come up with the better design of the life saving equipments. You can also help them with their operations and so on. So this complete list of CFD application is rather long, it's growing each day. Okay. Once you get involved with your research work in CFD, you will come across many such exciting applications. Each day you will come with one or many exciting problems. At the same time, I would like to forewarn you that please remember CFD is also a pretty demanding subject. Okay. It demands a thorough understanding of physics, mathematics and at least good knowledge of one computer programming language apart from a general knowledge of information technology. Now just briefly have a look at the references which you might be interested in. I'll just list you few books which if you are interested you can have a look at them. The first one is Computational Fluid Dynamics, the Basics with Applications by J.D. Anderson. This is one of the ways the title says, Basics with Applications is one of the most interesting and simple books on computational fluid dynamics. On the other extreme we have got Computational Fluid Dynamics by Chung Tae-jae, which provides a compendium of the current knowledge in computational fluid dynamics, and it and the textbook you can find is that of Fersiger and Perrick. And we will later on discuss one particular methodology for discretization which is called finite volume method. This textbook of Verstegen and Malalsekera would be particularly useful. In the next lecture we will also come across few more references. I will put across few more books which you might like to consult. So we will stop here today. In the next lecture we will have a look at few more introductory aspects of computational fluid dynamics.